Alright, you guys look a lot more comfortable than I, but let's get started. It kind of fucked my presentation just now, and I cleared my Nix cache beforehand, so it's gonna take a while to rebuild. So we're gonna start with the plain PDF of the presentation for now. First, welcome to Reverse Engineering U-Boot for Fun and Profit. I'm Zeno. Where's my mouse pointer? There, I have to scroll. Yes. Who am I? My name is Adrian or Zeno, what I want to call me. Where might you know me from? Probably nowhere. I like breaking stuff, I like tinkering, I like to bring stuff to do stuff it wasn't supposed to do. And yeah, like you see that sometimes bites my ass. And yeah, a short shout out to my employer. I work for Digiforce. It's a German Leipzig-based cybersecurity company. We do penetration tests, we do SOC, we do forensics, we do software development and security research. This is where I come in. So, and another shout out to Bartosz, tried to listen to me trying to troubleshoot shit that didn't work or that didn't make sense for me. So, yeah, let's continue. What is the talk supposed to be? I meant it to be a field guide, so I wanted to share tips or tricks that I wish I had when I started this whole project, and I want this to be as live as possible, so if anybody has questions, just raise your hand, shout it. I think we can figure something out. And yeah, okay, let's get started with this whole thing. But first, how did we even get to this project? I'm sure you read the description. We're talking about a babyphone here, but it all started by a colleague, Bartosz, and me having some downtime at work and thinking about what we can do. And so naturally we thought, what's insecure and has a really big scary factor? So obviously we went to Amazon, searched for baby monitor, sorted by best reviewed. We're sure there were some steps between sorting by best reviewed and buying the first product and actually gaining profit from it, but we were sure it wasn't too involved. The problem is, apparently, they actually gave a shit, which is a problem. But what are we even talking about? We're talking about an IE Geek baby monitor baby 1T. What does it look like? You can see it here. It's a cute little bunny. I will show you a physical example, but it's kind of taken apart, so you have to work with this image there. Basically, it can be controlled via an app or via a handheld device. It supports Wi-Fi and radio. It has a microphone and a speaker. It has night vision, 355 degrees of rotation in stunning 720p. And it has a temperature and humidity sensor. This is the counterpart. It's the handheld device. It also has radio, so it communicates with the baby monitor itself. And you can tilt, zoom, pan, and yeah, basically it also has a microphone and speaker for two-way communication, just what you would expect from a babyphone. Ooh, I think it built my presentation. Let's actually try and see if this works, because it would be a lot nicer. But just 1 second. While this figures itself out, let's continue. Hello. So, okay. Basically, what did we want to achieve? We wanted a no-click exploit of the whole babyphone, but yeah, I think you can imagine how that went. Still a lot of work needed, but for that goal, first step, we of course need lots of logs, and a shell would be really nice, so we can attach a debugger or anything, mess with the device during runtime, which makes the black box security research a lot easier. And ooh, we can try again. PDF PC, result, slides. Does it work? Ooh, yes, perfect. Well, let's jump to the right place. And then we can continue from there. Yeah, perfect. Okay, so, and this is where this whole project started, and this presentation as well. Okay, let's start with recon, as you do with any security research project. Come on. Yes, we start with recon. And any embedded device has some kind of interface, so you can talk with it. That can be UART, can be JTAG, whatever. But let's open this thing up and take a look around the PCB. As you can see here, I marked it in red. Some of you can imagine what this is. This is UART. It means Universal Asynchronous Receiver Transmitter, and it can come in many different forms. For example, holes, pins, or any form of connector basically. Here we have the 4 holes in the PCB. The 4 pins are VCC, 3.3 volt, ground, RX, and the TX end of this whole thing. And yeah, if you, as we can see here, we don't really know the pinout of the whole UART interface because there are no markings on it. And usually you can figure it out with a multimeter and just some reading voltages. I had to cut it short because I was 1.5 hours when I originally practiced this talk, so I had to cut out a lot. If you want to know more about that, you can come find me after the talk, and I'd be really happy to talk about that. Okay, let's continue with the thing directly next to it. That's the SPI flash. SPI stands for Serial Peripheral Interface. It's basically flash storage that stores anything the device needs to function. That can be the bootloader, the kernel, the file system, configs, or like any secrets. So a really juicy target for reverse engineering and security research of the device. We can see here it comes in a SOP8 package. SOP8 basically means a small outline package with 8 pins. And if we zoom in, which we can do, it's an XMC XM25QH128C. This number doesn't mean anything, but we can look for a datasheet for it, which is then again really nice because you can get specs of the whole device and a pinout, which we later need. And the one last thing in the trifecta, it's the CPU. If we again zoom in, we can see it's an Ingenic T31 with an X-Burst 1 CPU. What does that mean? Ingenic T31 is just a system on chip, like your Raspberry Pi or your Apple CPU, and the X-Burst 1 is the CPU that powers the whole system. So now we figured all of that out, all of those devices, but how do we actually talk to it? This is the janky hardware setup of the talk. It looks like this. We have 2 Raspberry Pis because one wasn't enough, but basically we just have some clamps that we connect to the ports or the SPI flash and then to the GPIO header of the Raspberry Pi. We need 2 because we have 2 little 3.3 volt pins on one Raspberry Pi, so the second has to provide those. If you want to know more about that setup, also come find me after the talk because I was way too long. Let's get started with UART. It's the first live demo part, so let's try and see how that works out for all of this. Yes, alright, there's this problem. Oh, fuck my life. Let's close this. And it doesn't care about that. Haha, almost. Yes, great. Let's jump over here. And yes, it worked. Perfect. Okay, let's go to babyphone. Babyphone, camera, logs. There are a few more log files here, but don't let you spoil yourself just yet. We need the bootloader silent. Okay. Basically, I also would have done this live, but again, time was a little short, so you're just gonna have to live with the captured logs. As you can see here, we are running a U-boot SPL 2013-07. What does that mean? SPL basically means it's the first stage of the U-boot boot process. U-boot usually boots in 2 stages. This one is the first. It does some initialization, which is great, loads something into memory and jumps there. And this is our real boot. That's the second stage. This is running from memory, so this is where most of the stuff happens. We can see it's an Ingenic X-Burst T31 SOC, which is great, we already know that, but now we have confirmation. Some memory address we don't care about, and then it detects our flash, which again, we know what it is, but it's nice to be confirmed. Here we can see hit any key to stop auto boot. This is a fun part of U-boot that allows you to drop to a shell during the boot process, which then allows you to mess with the pre-boot environment, or yeah, anything like that. And then it sends the probe request to the SPI flash, it detects the flash again, and then finds the Linux kernel image and tries to boot that. We can see it's the Linux 3.10.14, okay, great. And then it starts the kernel, and after that it goes quiet. Which sucks, because we really needed those logs. And like, maybe we could stop the auto boot and configure like the kernel arguments or whatever, but I can tell you we already hit some keys in this boot log, but it doesn't actually work. U-boot doesn't want to accept those key presses to interrupt the auto boot. Now, if something were to happen to the flash during the boot process, who knows what might happen, so let's actually try that. Basically, like I said, it's an SPI flash chip and it has 8 legs. So if we short 2 of those legs together during the boot process, it fails to communicate with the flash chip, and actually drops us to a shell, because U-boot in that case doesn't know what to do and says, okay, better let a human figure that out. Let's go to the shell because I can find the image I'm supposed to boot. So let's take a screwdriver, put it between those two pins. If somebody wants a live demo of that, you can also come find me after the talk. And okay, let's actually do that. We can see, okay, we have our first U-boot stage, some extra logs you don't really care about. It loads into the real U-boot in memory. Again, all the same stuff. It has the auto boot line again, which again doesn't work. But now, instead of saying, yo, SPI probe, it says unsupported manufacturer 00 failed to initialize SPI flash, and wrong image format, can get kernel image, and it drops us to something that looks like a prompt. The problem is it only looks like it because it has this weird password thing in front, which means this is a password protected U-boot shell. And some of you might actually know U-boot doesn't have that feature. Well, it has some kind, but you have to hit the right key sequence during the stop auto boot prompt and not of the actual shell. Which, okay, cool. Now we're back to square one. We can't actually change some kind of boot arguments, and we don't have any kind of how it's called? Yeah, we don't have any kind of logs and no shell access. So, okay, fuck. What can we do? Let's go back to the presentation again and jump forward. I'm terribly sorry that this is so slow. I wasn't prepared for this setup. Yes, we're almost there. Almost, if it catches itself, which it doesn't seem to do. Okay, then I'll talk a while this figures itself out. U-boot, like I mentioned, kernel arguments for a bit now. What does that actually mean? Oh, perfect, it worked. Yes, we got information, we got a shell, but we only have boot logs and the shell is password protected. But now, like I said, I talked about kernel arguments a lot and boot args. What actually do I mean about that? The Linux kernel, when you boot, has the support for specifying kernel options, kernel arguments on the boot command line, which then configures some part of the kernel. Some of you might have encountered it via configuring quiet boot for Linux or something. Basically, kernel args is the equivalent to boot args in U-boot. In U-boot, in order to set the kernel arguments, you set the boot args variable in somewhere during the U-boot process, and then it passes those on to the kernel itself. So, in order to confirm that, let's get to flash dumping this whole device. Basically, what does this allow us to do? It allows us to confirm the boot args, but also, like I said, the kernel or the bootloader image, and it gets us the file system and like the whole user space, which again is really fucking nice for reverse engineering. So this is how dumping the flash looks, well, in theory. Basically, like I said, it's a SOP8 flash chip, and so we need a SOP8 clip, obviously, to flash that. You can get those on Amazon, on AliExpress, whatever favorite marketplace you have. Then you best get a Raspberry Pi because that worked in our testing. Everything else just failed in weird ways. And you use flash ROM. Flash ROM is used by the corporate project, I think, in order to flash BIOS chips. And here it allows us to interact with the flash, like reading or writing. This is the command we need. Basically, we instruct flash ROM to read to the specific file. This is what the -r/dump from working.bin does. And we tell it to please use the Linux SPI driver with /dev/SPI-00. What is /dev/SPI-00? Basically, it means this is the place where the Raspberry Pi exposes its SPI interface located on its GPIO. Now, after we run that, it will calculate a little bit and then drop us a nice 60 megabyte flash binary file, and this is where we get to extracting U-boot, because U-boot needs to have those values hard-coded somewhere in order for them to actually be picked up during boot and applied to the kernel command line. So, yeah. Now we need to somehow extract U-boot from this whole image, and I think I have to... Oh, no, it works. Whoa, I'm surprised. Alright, basically, we have this file here, dump from working. This is what we just dumped with a flash ROM. So now, in order to extract U-boot from it, we can actually run bin walk over this, dump from working. And we get a nice little table of what is located in this binary. Binwalk is short for binary walk, I can imagine, and it basically analyzes random binary files and scans for magic values, magic bytes, and then gives you a nice representation of this. This hasn't always looked this nice. During our work on this, there were a lot of false positives, but then they rewrote it in Rust and it worked. So take from that what you want. What do we see here? Like some U-image, firmware image. This is the header format that U-boot uses in order to load the Linux kernel. And a little bit further down we can see two file systems, which isn't too unusual for embedded devices, but this is not what you want to talk about, because nowhere in this listing we actually see U-boot, the U-boot binary itself. But there is like some suspicious space at the beginning of the binary where it didn't encounter anything. Just a CRC32 polynomial table, whatever that does there, I don't know. But we can see from 0x0 to 0x40k, nothing happens. And it would make sense to assume that our U-boot actually lives there, because it's nowhere else in the listing, and the bootloader is practical to have at a known offset, which in this case would be the place where the SPI flash is mapped into memory. So let's just extract that binary part of the binary file and take a look at it. How can we do that? Usually Binwalk would support you to automatically. Yes, there's a question. Can we get a microphone there, maybe? Oh, it's hard to read. Okay, we can try and zoom in a little bit. Is that better? Not really. Well, this sucks. What can I try? A highlight, yeah. We can try that. Well, the problem is we need to do a lot of other stuff. Where highlighting will be difficult, but we can try. Okay, like I said, usually Binwalk will try to do that itself, the extracting, but because it didn't actually detect this file, the U-boot binary, it won't automatically do it, surprise. So let's do it ourselves. We take, okay, I highlight this instead of typing it out. Can everybody read that? Okay. Basically, here we instruct DD to actually take our working dump as the input file. Then it will tell DD to please output everything that we receive now into uboot.image. It uses a block size of 1. Why? DD usually operates off block sizes, meaning 4096 or whatever. But because we don't want to do some fancy calculations in our head and it's only 16 megabyte, we just set it to 1 byte. Please calculate blocks as 1 byte big. And then we tell it to please extract 40k bytes from that, because 40k is the offset of the next known binary blob in this dump. So we tell it, okay, please count up to that byte number and then put everything in the output file. If you run that, it should do some work, calculate, and it says, okay, I copied so and so much bytes, 256 kilobytes. Sounds great. Let's take a look at that with file. But if we actually do that, it only recognizes this as data. Okay, good. What did we expect? If Binwalk didn't recognize this file, probably also won't. But we now have the U-boot image. Now, we extracted U-boot, and now we need to analyze this binary dump. How can we do that? There is strings for cursor research. Strings just searches the binary for any amount of printable, human-readable strings and displays them to std out. Or we could use a hex editor for full analysis, which I prefer because it gives a lot more context around everything. But because this is only a short search for the boot args somewhere in the binary, we can use strings because we don't need a lot of context right now. So let's try and do that. We basically just type strings. U-boot, we pipe that into less, and then we get a big list of strings. There's a lot of garbage in there. Why? Probably because those just happen to be printable. And then we have a lot of this stuff, which we actually recognize from the boot log. So this seems reasonable to assume that this is actually our U-boot binary. Now, let's search through that. We search for boot args, because this is what we know the variable is called. And we can find this first, which would confirm some kind of conspiration. Console is the known Linux console kernel argument. because it configures the kernel where to actually log its output. And here we can see it output says to/dev/null, meaning of course it won't appear in the UART output. Let's search a little bit further. There are a few more hits. Change boot args, okay, we can't. And we get this hit, which looks a lot more specific than the first one, but still console equals /dev/null, meaning all our logs that we actually want to have disappear. Great. What can we do about that? Maybe just some kind of reverse engineering. But first, let's go on a short tangent and talking about open source. U-boot is a GPL project, meaning all modifications that happen to the binary to the source code need to be released to the public if the binary is also distributed to the public, which in this case obviously happens because I hold a babyphone in my hand that actually boots U-boot. So, like the good German I am, I wrote to them, can you please provide the source code because you kind of have to? And they said, no, we don't want to. Oh, it's actually quite readable. I didn't expect that. Basically, no, we can't because some kind of company security that is at stake. I don't fucking know. So I again wrote them, yeah, but you still kind of have to. And here is a link to the FAQ of the license, and here is a link to the license itself. And then they said, no, we can't. And okay, great. Like, what am I supposed to do about that? I'm pretty sure my employer doesn't want to go onto a legal battle with like a transnational organization. But I think it was low-level learning that said anything is open source if you can read assembly. So let's go do it ourselves. And this is how we get to the reverse engineering part of this whole thing. And I actually have quite a bit of time left, which is great. But first, let's recap a little bit. We know why we get no logs, but we still want those logs. And this is because the boot args environment variable of U-boot is configured in a way that we can't see those logs because they get logged to /dev/null. How can we change that? First, we could of course just straight up patch the binary and patch the boot arg somewhere in there, but this is really messy because our replacement string would be to be exactly as long as the original string or a little bit shorter, but then we would have to worry about null terminating it, which, yeah, like, it's not a great experience. And we would also need to flash it back. Yes? You in the back, yeah. Yeah. What's with patching strings? Sorry. Yeah. Oh, there's a microphone coming. This is great. 1 second. There's a microphone.
Oh, great.
Yeah, thank you.
I'd like to ask what you said. You said that you could change your boot arguments, like patch them.
Yeah.
You would need to have the same number of characters, or a little less.
Yes.
But you said that there is some problem with that.
Yeah.
What's preventing you?
Because if we replace it with a string that is longer,
yeah,
we actually overwrite data that is behind of that, which can have weird consequences, which we can't comprehend just now. So that would be the problem.
Okay, but if it has exactly the same length,
yes,
of original,
yes, then that wouldn't happen because it would fit exactly in place.
Okay, but what about checksums?
This is another part. We would also have to worry about checksums, but maybe there aren't any, but we didn't try that for now. So yes, we also consider that, but that wasn't a problem just now.
Thank you very much.
And there was a question in front? Okay, it was the same. Then thank you. All right. We could also change the boot args in U-boot itself in the shell, like I mentioned, but we already know that's password protected, so that's also a big problem. But let's get to reverse engineering because they implemented some kind of password protection custom, and like there's wisdom in software engineering, don't roll your own crypto, don't roll your own payment processing, and maybe don't roll your own authentication, so maybe they fucked up somewhere. So let's jump into Binary Ninja and take a look at that. Okay, we open up Binary Ninja and take our U-boot image that we just extracted from the flash dump, and it asks us about the platform and base addresses, Okay, we know the platform. We know we are running an X-Burst 1 CPU, which means we can Google, and it basically straight up tells us that it's an MIPS 32 processor, and we also need to specify the endianness. And we know it's probably a little endian because that's the standard for software. So let's actually select that. It asks us about a base address. We don't really know the base address because we didn't, the memory layout of the SOC wasn't really documented really well, or I couldn't read it. Both could be the case. And so we don't actually know where the flash lies in memory. So let's just take 0 and then 1 second. And there are some questions. Maybe we can get a mic there while I still talk. Perfect. So yeah, let's just assume it's at 0x0 for now, which probably isn't the case because no software really runs at 0x0 except a few exceptions. Okay, let's get to the questions.
You already know the base address from the logs from previous stage because it tells you where in memory it mapped it.
Yeah, we actually also tried that, and like we tried a few other things where just common base addresses, but those all didn't really work. Maybe I missed the right one in the logs, which would be really embarrassing for 2 weeks of work, but yeah. We also looked at those and tried those, but those didn't work mostly. There was another question back there. Okay, it was the same apparently. Okay, so let's take 0x0 and load this into Binary Ninja. I hope this is readable. Yeah, mostly. Okay. Now Ghidra Binary Ninja starts analyzing, and we can see there's a lot of zeros at the beginning, which, okay, this is fine. But somewhere down here we actually get some function disassembly. And I can tell you this actually corresponds to U-boot fork, which we found. There are some... Yes?
Sorry, can you try by any chance light theme on that?
We can try, if I can actually figure out how to do that. Refresh themes probably isn't it. Does anybody know where I can change the theme? Command palette. Where? Control-Shift-P? Doesn't want to accept Control-Shift-P. But there was command palette here. Control-P. And then settings. Yes, that makes sense. Theme. Slushy light, I'm sure, will look great. Ah, great. Thank you. It really helps with this whole part of the presentation. All right. Like I said, there is some kind of source tree for U-boot and the kernel that actually exists for injecting T31 SOCs. And by looking at it and like comparing some straight up constants, I confirmed that this is actually the start of the whole U-boot binary, which is great. So this seems to be actually our U-boot binary. But no, we want to look at the password prompt and try to change that. If we can do that by just inverting the condition, it probably is a string comparison between the actual input of the user, maybe some hashing, and then a comparison. So we could go to the place of the comparison, invert the condition, and it will accept all wrong passwords except the actually right password, which would be an option. Or maybe they just left a string in there, but okay, let's search for password. We search for password, and we go there. And usually in the bottom here, it's white on white, there would be cross-references. But as we can see, this little box down here is empty, so we don't get any cross-references. And if we take a look at a few other strings, like this error string or this FCG or this interrupt thing, all the cross-references are empty. So this might actually have something to do with the base address, but we don't actually know the base address now. Okay. What can we do? We know we're running U-boot, and we know U-boot runs in 2 stages. The first stage, which runs from the flash, and the second stage, which runs from memory. And yeah, we know where U-boot loads the second stage into memory because it was in the logs, but if you rebase to that, it doesn't actually work. So we have to go a little bit further. what can we do? We know we have the U-boot source code because, actually, let me go there. Projects, 3 babyphone, camera code. And in here we have ingenic U-boot. This is the source tree I cloned from GitHub, which implements some part of those socks. And we have the source code. Great. And now we need to find some kind of function that uses a lot of strings so that we can find it in disassembly and then figure out why stuff doesn't work. Because you have a lot of strings, you have a lot of data that we can cross-reference or figure out why it won't display those strings. Now I sat down and looked through the source code for like 20 minutes, but I want to spare you those 20 minutes because we still need to do a talk. So let me actually spoil that. We are looking for timer.c in xburst. Xburst timer.c. Oh my god. Home/project. Sometimes it just switches working directory, which is great. Code. And now we can open xburst/timer.c. And this is specific to CPU, which is great. And we get into this file. And timers are great because those are used a lot in embedded devices. And embedded devices also have a lot of constants because they need to configure memory map registers or need to configure some kind of subsystems which often require hard-coded magic values and constants. So let's look through this file and we find this function, reset timer. We can see it uses 3 constants, which is great, and it writes them to some kind of memory address. And writes are also great because writes in C or like some kind of high-level language often translate relatively close to actually assembly instructions because mostly it's just a move or a load instruction. So, okay, let's start here. We know we have TCU, OST, and CNTH. TCU probably stands for Timer Control Unit. So let's look for that. TCU, OST, CNTH. And we can see there are a lot of ARCH, T something, but we want ARCH T31, which is here. Great. Let's take a look into that file. There are a lot of constants, which is also great for us, but we can see OST CNTH is 0xe8, which is a really small value and probably very hard to find in the actual binary because it's only 1 byte big. So, not so great for us, but let's also take a look at TCU write-L. How does that actually work? We can find it at the beginning of the file, and it's this line. And we can see it takes the input and writes that to a TCU base plus an offset. And the offset is passed as an argument. Okay, let's take a look at what a TCU base is. TCU base is, we can grab again through the code base we actually found. TCU base, and it's some called base.h of T31 somewhere. TCU base. Hello. And yeah, there's ARCH T20. So again, those offsets are used in a lot of definitions, which is obviously not really great for actually finding it. So we need to find the right file. Again, this doesn't really take long, so just grabbing through the code base a bit, this is done relatively quick. Okay, here we go. T31 base.h. Yes, I don't have Clang installed. And we can see it's a really long value, which gets added to the very small value, so in the end we get a really big value. Which is great, because very big values are very specific in the code base, because they obviously don't appear as mesh. So let's take this value and take a look into Binary Ninja, where we have a nice integrated Python console, and add that to our offset 0xe8, I think it was. Let's take a look again, and it's in here. Okay, it's 0xe8, so let's actually add that. And we want this as a nice hex string because it makes searching a lot easier and for us to remember it a lot easier than some big binary. Okay, we take this and put this into the search function of Binary Ninja, and it finds 2 hits, which is really small because I am zoomed in really much. Yeah. Okay. Great. We can see we get 2 hits for this function. And the first one is at 9FC and the second one is at 6CB0. Because we know this is used in reset timer, which is probably used as well in the first stage and in the second stage because timers are needed everywhere. And so the first one is relatively at the beginning of the binary, so it would be safe to assume that this is actually the first stage that uses this, and the second one is the second stage. So let's look into this, because we know the password check actually happens in the second stage, because we saw those logs. It first loaded the second stage, and then the password check happened. So let's give this a name. You know, this is reset timer, exactly. And we can see we have 3 writes, and all are set to 0, which looks really close to the code we have in timer.c down here. Now, one thing that is nice to know, things often get inlined, and things close in the source code are often close in the binary. If you take a look around, we can see there's also get timer and timer init, which looks like this, some value, a reset, call to reset timer, and again 2 writes. So let's go into Binary Ninja, look around a little bit, and we can see this here looks like timer init, because again we have a write of a value to a memory address, and again 2 other writes to something that looks like something with the TCU base, and we have the reset timer call here. So let's look a little bit further down. Can I make this a little bigger? Okay, we have this function here. This doesn't look immediately familiar, but if we take a look, we can see there are 2 reads from a memory address with TCU base, and like some if condition, and then a subtraction. Now let's go into the source code, and if we take a look at get timer, we get 2 reads and then something small. So this is not a very big function, and we take a look at the get timer function, which is an LLDiv, which calls get timer 64. So actually get timer 64 might actually be inlined because it's not very big, and we have subtraction. This looks relatively close what we actually saw, except there isn't a if statement. There isn't branching anywhere. So let's take a look what LLDiv actually does. It's in here. So we grab to the code base, we see LLDiv. It uses the do-div macro, which has a branch in it. And this branch calls another function. So okay, let's go into Binary Ninja and confirm that. We can see we have those reads. We have the subtraction, and somewhere in here there's a branch with a function call. Now, decompilers often like to invert branches, so this looks like our get timer, which is great because timers probably are getted a lot in embedded programming. So let's actually look through the code base for where get timer is used, and where we can find a function that uses it, which also uses a lot of strings. Now, again, I want to shorten this up a bit, so let's open fs/fs.c and go to do load this function here. You can find it by just grabbing through the code base. And down here we can see a call to a get timer, an fs read, and again a get timer. So this is the signature we're looking for. We want 2 calls to a get timer, which are relatively close together, and a single function call in between. So let's open up our reverse engineering tool again and look through the cross-references. Yeah, okay, this is only 1 call, so probably not what we are looking for. Those are 2 calls, but if you jump there, there's a lot between, which we don't actually care about. And then here, it's way too much. Again, here, there's stuff between. And if we scroll all the way down, we get to this function. This looks exactly like our pattern. We have 2 get timer calls, and in between we have another function that actually is called. So let's just confirm that. We know we have, can I actually split this? No, that's not gonna work. Let's split this. Okay, we can see in the beginning there is this if statement which checks the argc count that is passed to the function. And then if it's less than 2 or bigger than 7, it just returns an error. So let's go into Binary Ninja, take a look at that. Up here, there is this check happening. argc is less than 2 and arg3 is bigger or equal than 8, so essentially bigger than 7. And we return some kind of error. We can assume this is the error. So this pretty much looks like the function we are looking for. So decompilers work using heuristics and taking a look at assembly patterns and trying to translate them back to higher level code. And they can do that a lot better the much more information they have. So let's actually try to give Binary Ninja as much information as we can. And the good thing is we actually have the source code, so we can actually do that. We can start by taking function signature, which would make our which provides a lot of information that we can actually need. We press the Y key and it opens up this change type submenu for the function or the variable. We paste it in. It complains about some issues, which is totally fine because first there's this humongous space in here, and then we can see at the beginning it once expects the command table T, which we obviously can't provide, but because it's a C, we just make this a void pointer and it should be happy and nothing should break too much. So now we can see and also use those arguments in the disassembly, which makes stuff a lot easier to read. And now for ourselves and for the sake of providing more information, let's just rename a few other things so we know render out this function. And yeah, okay, so I think we're going to shorten this a bit because in this setup it's really hard to constantly switch between those things, and I think it's really hard for you to follow in that case. So let's just go to the end here. We can see there's a printf, an if condition, a few puts, and then a set env hex. Now let's take a look at those, the end of the function in Binary Ninja, and we get our getTimer calls, and actually we can check because between the getTimer things we get an fsRead, and that is assigned to lenRead. So let's do that in Binary Ninja. We rename this to fsRead. Hello, fsRead exactly, and those get provided to lenRead, and we know that this is time because this is how it's spelled in source code, and this is also time. So let's rename that. Yes, I know what I'm doing, and now we get those mentions down here as well, which makes reading this a lot easier. So we know there's this thing after that takes the lenRead and other argument is probably our printf because it takes lenRead, another argument, and it uses a format string because this is what printf doesn't see. If we take a look at this, this is supposed to be our string. It isn't there, which explains why I don't get any cross-references because Ghidra can't resolve those. It tries to locate those somewhere at 0x80 something, and obviously our binary is loaded at 0x0, so it probably will never reach that point in the memory, so it can't get those. Okay, great. Let's rename this to printf. Printf, I mean, void printf. It takes char star arg, the formatting string, and then it's a variadic argument function. So let's specify that as well. And we can see it actually figures out the last argument to be time, which seems to confirm this is actually our printf we're looking for. So we know that the printf at this point wants to call %d bytes read in %lu milliseconds. So let's try to find that ourselves. So we know where it is actually located, and maybe we can derive something from this. So let's go to the string search, bytes read in, and we can see, okay, it locates this, but at 0x359f4, which obviously is a whole lot of way between the actual load address where it expects it to be and where it's actually loaded in memory. So let's just jump there, and then Binary Ninja has the thing, copy address. Let's copy that, put that in here just for safekeeping, and then we go back and we take this address and put this in front. So like we get the offset where it actually, how much we missed the address. Let's again print it as an hex, and we get this address, which looks a lot like some kind of base address. So actually let's put that into analysis and rebase, put it in here, and then we'll do some stuff, and we actually get string references. And this makes our job a lot easier now, because now we can just look for password and hope there are some cross-references for that as well. Let's do that. We go to password, we jump there, and we see this looks different now, and we can see there's actually cross-reference. So let's jump there, and okay, this seems to be the read or like the prompt. We can tell us, yes, this is a string. And then let's look down here at the break, because this is a while loop. If you want to break out a password prompt, this seems to be our string comparison, and in the back there's something called PPS password, which looks a lot like a password that you should use in a production system. So yeah, if we take a look in this function, we can see this looks like some kind of string comparison, great. And now, after 2 weeks of bashing our head against this base address problem, because there were a lot of more steps involved in between actually us finding this, we SSH into our Raspberry Pi, connected UART probe, and went again jamming the screwdriver into this thing, into the SPI flash, and then we opened up screen and came to logs. Let's go there, and then bootloader unlocked. Let's go there. Okay, we get our booting, normal stuff. We already know that. We skip the hit any key to stop auto boot. We jam the screwdriver in there. We get to password, type in PPS password, and as you can see, ISVP T31 hashtag. We can type help, and it actually prints out U-boot commands. So this is how we actually cracked the password, which wasn't really cracking because there wasn't any hashing involved. Like I said, maybe don't roll your own auth if you don't know what you're doing. And yeah, this is how we got to actually getting the password. We got a shell. IEGG is probably in violation of the GPL. I'm not a lawyer. But the only problem still left remaining, there's still no profit. So thank you for putting up with this kind of a shit show of a talk. Like I said, I had to cut out a lot of stuff, a lot of the actual physical stuff with connecting to the SPI flash or the UART. But if you're interested in this, come find me after the talk. You can contact me under all the stuff up there. My email, my FADI, my web, or my DEC number, and I'd be happy to talk about this a little bit more. Thank you. So, if you still have any questions left, then I'm happy to answer those as well. Otherwise, okay, maybe not.
Are there any questions? We had some during the talk, but if not, we do have some questions right there.
Perfect.
Can we get the mic?
First of all, thanks for the talk. Assuming they would have used hashing, so there was no simple string comparison.
Yes.
Would it be similarly complicated to break that as it would be with the binary strings, the replacing, because you said it was messy?
Actually, Binary Ninja supports this patching feature of branches, and I think it results in the same size, so that actually would have worked in case only if they didn't use any checksums. But yeah, we like I said, we didn't test for checksums, but this might actually work. Yeah.
Thanks. We have another question right close there. Go ahead.
Did you find any bugs yet in the firmware?
No, we didn't actually get to that. We made some strides and actually got to the root shell of the device. After working around the password prompt in U-boot, we could patch those boot arcs, and that actually enabled us to get to the Linux user space. But getting a shell there was again a little bit more involved. But again, I'd be happy to talk about that a little bit more. But no, we didn't actually get to working on the firmware just yet. Yeah, you have a question again.
When you were patching the boot arcs to get root, was that done like statically or dynamically with the U-boot shell?
With the U-boot shell. Patching was a little bit the wrong word here. Anybody else?
We
There's
have
one
another
down here.
question over there.
In the first stage, you talked about that the console is redirected to dev null. Would it maybe be possible just replace this arc with the white space, assuming that you would skip this. So are you aware whether there are any checksums in the binary?
That would probably work. I don't exactly know what the default is for the console argument. Again, we didn't get to that because we also had a few troubles actually flashing back the firmware, but not because some checksums. It just failed silently, even if we didn't change anything. So yeah, that's a whole other thing.
Thank you.
Do we have any other urgent questions? Or not so urgent? We still do have a couple of minutes, so if you have questions for Zeno. And if not, I believe you can catch Zeno around Congress and via all the socials that were mentioned here. So thank you so much for taking us through this adventure. And I know that Profit is not on the agenda yet, but hopefully sometime soon by next year.
Maybe.
So if you could join me just giving a big thanks to Zeno for this nice adventure through the ups and downs of hacking babyphone, and yeah, thank you so much for your time, and let's give him a nice big round of applause.
Thank you.